Everyone, in this video we are going to talk about primality testing. So primality testing is a topic which we need in public key crypto system, especially in RSA, because in RSA we need to select large prime, so we need to check that whether the selected number, large number, is a prime number or not. So for that purpose we use primality testing. So basically the purpose of primality testing is to know whether a given number or whether a chosen number is prime number or not. So how to check whether a number is a prime number, or how we can define a prime number. A prime number P is only divisible. A prime number P is only divisible by 1 and P. Only divisible by 1 and P. It means if a number is only divisible by 1 and itself, then we can say that number is prime. So we need large prime numbers for RSA algorithms. So we need large primes like P and Q. So for example, we need to select a 1012 bit prime. So this P and Q will be lie between 0 to 2 to the power 1012. So it is really a very large number. So how to generate such a large number, such large prime number, and how to verify that this is a prime number? So first one is, there are options. First one is the naive approach, like we choose an integer P and then test whether it is a prime number or not. So this is called a naive approach. So in naive approach, what we do, let's say we select a number P and we are going to check from 2, 3, 4 up to P minus 1 whether it is divisible by these numbers or not. Whether, let's say these A belongs to this, and we are going to check whether A divides P or not. Or we can check whether A is greater than root P or not. If A is greater than root P, so we can check it for A divides P or not, because because A dot B is equal to P if B is less than root P. But this is not a good approach, because it will time complexity will be much more for this approach, because P is such a really large prime number. So this approach cannot be accepted. This is a very large complex approach. Now we have sieve approach also. Sieve approach says that delete the composite, remaining are prime. If we delete all the composite, then remaining are prime. Delete the composite. It means, for example, between 1 to 100. If we delete all the composite numbers between 1 to 100, then the remaining will be prime numbers. Delete the composite, then remaining are prime. So how we can do that? Like for example, first we are going to delete multiple of 2, like 4, 6, 8, 10, so on. Then we delete multiple of 3, multiple of 5, it will be 5, 10, 15, 25, so on. Then delete multiple of 3, so it will be 3, 9, 15, so on. Then multiple of 7, because multiple of 4 is already deleted with multiple of 2, multiple of 7, and if we have deleted multiple of 3 and multiple of 2, already we worked on multiple of 6. So we can do it like this, but it is not a very efficient approach, because P is going to be a very large number. Okay, so this is also not a very efficient approach. So then we have some tests, like for example, first one is Fermat's primality test, which is based on Fermat's Little theorem, and we have already discussed Fermat's Little theorem. So what Fermat's primality test do? This Fermat primality test, if a number is not a prime, if a number is not a prime, then it will definitely give us that it is not a prime, it is a composite number. This is a definite test. But if a number is prime, like if a number is prime, then it can give us that it is a prime, or it can also not give us that it is not a prime. So it means it is going to give us pseudo prime numbers. And this Fermat's little theorem is based on this Fermat's primality testing. It's based on the Fermat's little theorem. So what is the statement of Fermat's little theorem? Let P be a prime and GCD of A and P is 1, or you can say A and P are co-prime to each other, then A to the power P minus 1, this is Fermat's little theorem, then A to the power P minus 1 is congruent to 1 mod P. This is Fermat's little theorem. So this is a necessary condition for P to be prime, but it is not a sufficient condition. This is a necessary condition for P to be prime. So if a number does not satisfy this condition, that it is definitely not a prime number. But if a number satisfy this condition, then we cannot say that it is prime or not. So it means it is a probable test, it gives us probable prime. So if condition satisfies, then we can say that P may or may not be a prime. Okay. But if the condition does not satisfy, then we can definitely say that P is not a prime number. So how we are going to test this? So their algorithm is choose an A. For example, we are going to test for P. So choose an A such that A is less than P. Now compute GCD of A and P. Compute GCD of A and P. If it is greater than 1, then P is a composite number. Then return. Okay, I can write it here. Compute GCD of A and P. If GCD of A and P is greater than 1, then return P is a composite number. Else A is co-prime to P. Else A is co-prime to P. Then what we are going to calculate? We are going to calculate Y, which is A to the power P minus 1 mod P. If this Y is not congruent to 1 mod P, then return P is composite. Then also P is a composite number because it is not satisfying Fermat's little theorem. Else return P is a prime number. Else return P is a prime number. But this P is probable prime, or you can say this P is probable prime base A, because this P is prime only for this A which we selected. Only for this A it does not have any kind of GCD with this A is 1. There can be another A for which it is not, we cannot find that it is GCD is 1 or something like that. So that's why we say that P is probable prime base A. That's why we say that P is probable prime base A. Let's check it with the help of an example of Fermat's Fermat's primality testing. Let's say P is 49. So this is an example. So again I take a number which is small so that we can demonstrate example easily. Otherwise it is for large prime. And we select some A. Let's say A is 19. Now GCD of A and P. GCD of A and P, how we can calculate GCD of A and P? We can calculate it with the help of extended Euclidean algorithm. This we have already done in previous lectures. So GCD of A and P should be 1. So yes, GCD of A and P are 1. So it means A to the power A P inverse is congruent to 1 mod P. So this GCD of 49 and 19 comes out to be 1. Now we are going to calculate A to the power P minus 1. So 19 to the power 49 minus 1 mod P. So it is 19 to the power 48 mod 49. And when we solve it using modular arithmetic properties, it comes out to be 1. So we can say that 49 is a prime base 49 is a prime base 19. However, we know that 49 is not a prime number because it has a multiple 7 also, 7 into 7 49. So now we know that 49 is a prime number, but according to this algorithm, this is giving us that 49 is a prime number. So it means this is a probabilistic, like probable prime. Same example, now let's say if we select A is equal to 31. If we select A is equal to 31, then A to the power P minus 1, 31 to the power 48 mod 49, again it comes out to be 1. So it says that 49 is a prime base 31 also. 49 is a prime base 31 also. Then let's say for another A, let's say is equal to 5. So 5 to the power 48 mod 49, which is not equal to 1. So now it is saying that it is not a prime number, not prime. So if for any value it says that it is not a prime number, that is deterministic. This is deterministic. But if this testing says that this is a prime number, then this is probabilistic, or this is a probable prime, or such type of primes are known as pseudo prime number. They are not definite prime numbers. They are prime for a particular base. So prime numbers are always odd numbers also. So there is another test. This is Fermat's. So the most used algorithm is known as Miller-Rabin Primality Testing. We will check that also. So the second one is Miller-Rabin Primality Testing. Miller-Rabin Primality Test P. So let's say what this test say. So we all know that prime numbers are always the odd numbers, and even number cannot be a prime because that will definitely be divisible by 2. So let P be a prime which is also an odd number. So we can say that P minus 1, so as soon as I write P minus 1, it becomes even because P is odd. So as soon as I write P minus 1, it becomes even because P is odd. So P minus 1 is always equal to, because it is an even number, so it will always have a multiple of 2, even k is equal to 1. So 2 to the power k m. Let's say this is equation number 1. So we can write P minus 1 as 2 to the power k m. Because this P minus 1 is an even number, so it will always have a multiple of 2. So GCD of 2 comma, where 2 is where this 2 should be co-prime to m, because if 2 is not co-prime to m, then this will be k plus 1, another k plus 1. So these 2 should be GCD of 2 comma m should be always 1. So this is one thing. Now from Fermat's theorem, what we know, a to the power p minus 1 is congruent to 1 mod p. This is we know from Fermat's theorem. If we take square root of this number, then how we can write it? A to the power, if we take square root of this, if we take a square root of this, then we can write it like a to the power p minus 1 by 2 is congruent to plus minus 1 mod p, because now this is the square root of 1 plus minus 1 mod p. And let's say this is equation number 1. This is from equation number 1. We can write now, if we use equation number 1 here, from equation number 1, p minus 1 is 2 to the power km. So we can write a 2 to the power km divided by 2, 2 to the power km divided by 2 congruent to 1 mod plus minus 1 mod p. Or we can write it a 2 to the power k minus 1 m, 2 to the power k minus 1 m is congruent to plus minus 1 mod p. Or we can also write it like this, a to the power m to the power 2 to the power k minus 1 is congruent to plus minus 1 mod p. Even if p is a prime number and a is positive integer less than p, then a square mod p is going to be 1 if and only if either a mod p is 1, either a mod p is equal to 1 or a mod p is equal to minus 1. If any one of the conditions satisfied, then only a square mod p is going to be 1, even if a is a prime number and a is positive integer. So this is given by Miller-Rabin primality test. Now how we are going to do that? So how we are working on this? Let's say a to the power m is, not congruent to plus minus 1 mod p. So let's take a number b. Let's say this a to the power m is equal to b. Then b square is equal to minus 1. So then only it will be like, even if it is congruent to 1, then only, even if it is a square mod p, then only it will be like either a mod p is 1 or a mod p is minus 1, then only it will be like congruent to that a square mod p is going to be 1. Now how we test this? How we do, like, write this algorithm? We choose an a or select an a. We are going to compute GCD of a and p, a comma p, and this a should be congruent to p. Then we are going to calculate b, which is a to the power m mod p. If this b is congruent to 1 mod p, then return p is a prime, or you can say then return p is a probable prime. Then return p is a probable prime, or p is prime base a. Otherwise, we are going to check for all the numbers like from I to k minus 1, because this is the power k minus 1. So for I is equal to 1 to k minus 1, if b is congruent to minus 1 mod p for all numbers, then return p is prime. Then return p is prime. Still it is going to be a probable prime. Then return p is prime. Else, if b is equal to b square mod p, return p is composite. The composite is deterministic test. Return P is composite. So now here we are going to check for all I from 1 to k minus 1. Let's take an example for this Miller-Robin algorithm, and let's take a prime P which is 105. So we are just assuming that this P is prime. Otherwise we all know that P, we can write 105 as 3 into 5 into 7. It means this is not a prime number, but just to check the algorithm we are assuming that, let's suppose this is a prime number. So what is P minus 1? P minus 1 is comes out to be 2 to the power k into m, and it comes out to be 104, and it will be 2 to the power 3 into 13. So here k is equal to 3 and m is equal to 13. So when I say k is equal to 3, it means now this loop is will work from 2 times, 1 to k minus 1, 3 minus 1, 2. So now a is equal to 8. Let's select an a is equal to 8, so that GCD of a comma m is equal to 1, or GCD of 8 comma 13 is equal to 1. Now 8 to the power 13 mod 105 comes out to be 64, which is b square. So 64 square mod 10p is equal to 1. So 64 is a square root of 1, hence 105 cannot be a prime number. Hence 105 cannot be a prime number. Hence 105 cannot be a prime number, because it comes here. When we say that it is a b is equal to minus 1 mod p, then b is equal to b square mod p, return p is composite. So it comes out to be like this, so it means it is cannot be a prime number. Now let's check for another number. Let's say p is equal to 49. Okay, so p minus 1 comes out to be 48, which we can write 2 to the power 4 into 3. Now this 3 is m and k4 is k, and let's say a is equal to 18, so that 18 and this 3 is 18 and this is co-prime to each other. Now 18 to the power 3 mod 49, which comes out to be 1. So here we can say 49 is base, 49 is a prime base A. Here, this one, prime base A. Now for I is equal to 1 to k minus 1. 19 cube is equal to 19, because we are just incrementing mod 49. For a is equal to 19, 19 cube mod 49 is equal to minus 1. So 49 is a prime. Again 49 is a prime base A. So these are pseudo primes. Now let's suppose a is equal to 5. So 5 cube mod 49, it comes out to be 27. Now next time 27 square mod 49, we are learning the for loop. Mod 49, it comes out to be 36. Now 36 square mod 49, it comes out to be 22. So 3 times we will run the loop, and this is not a, it says that 49 is not a prime. So whenever we check for composite number, these two algorithms gives us the deterministic test, and whenever it gives a prime number, that is a probable prime. So this is how we are going to choose how we are going to remove the composite numbers, how we are going to choose the prime numbers in RSA algorithm. So basically we are using Miller-Robin primality testing for all types of tests. Sometimes we use format-listed test also. Otherwise exhaustive approach or naive approach or the sieve approach is very large, time complexity is very large. So in the next video we are going to check another crypto system, public key crypto system, that is called algorithmic crypto system. Thank you.